For my final presentation, I'd like to give you a little bit of a better sense of how backpropagation works and its amazing powers. So we're going to start with a simple function with two variables, x and y. And first we're going to look at how you were probably taught to calculate gradients in school. Just as a reminder, gradients are the derivatives of a function with respect to all of its variables, in this case both x and y. So you'd start, in our case we're going to start with our tree representation of the expression. And we're going to start at the root node, which is multiplication. And if you recall, the rule for differentiation when you're dealing with multiplication is we take the derivative of the left side times the value of the right side plus the value of the left side times the derivative of the right side. And then we just traverse down our tree. We have dx equals 1 on the left side. On the right side, the rule for addition is we just take the derivative of the terms and add them. And we calculate those values and then substitute all this into the expression at the top. And this gives us y plus x plus x. The problem is we now have to go back and figure out what the derivative is with respect to y. We've only calculated the derivative with respect to x. And so this can be really time consuming, especially if there are a lot of variables in our function or if it's a complicated function. So this is the naive method. With backpropagation, what we do is we calculate the derivatives for all the variables in one fell swoop. So we're going to start with an error value that we initialize to 1. If the output of this function was a matrix, it would be a matrix full of 1s. And the rule for multiplication is we're going to, for the left-hand side, multiply the error by the right-hand side. And for the right-hand side, we're going to multiply the error times the left-hand side. This rule might seem kind of arbitrary, but if you think about it, it's actually closely linked with the rules that we used on the previous slides. And for addition, what we do is we just send the same error down both branches of our tree. And to calculate the gradients for all of the variables, so for x, what we're going to do is we're going to add up the error at each of the x nodes. So we've got y plus x on the left x node and 1 times x on the right x node. And then for y, we just have one node, and that's going to have a derivative of x. There's one other optimization that backpropagation uses. We calculate the output of each node in a single forward pass and cache it at each node. We save that value at each node so that values like y plus x don't need to be recomputed during the backward pass. So to illustrate the amazing power of backpropagation, we're going to have a four-way race. We're going to need a pretty hefty function to demonstrate the difference in performance. So I'll be using the LSTM that I built on a randomly generated data set. In my previous presentation, I demoed the ability of my program to optimize functions with a single tunable parameter. This time I'll be using a function with 13 tunable parameters, each containing 20 by 20 matrices. So performance is going to really be critical for this. So our contestants from left to right are, on the far left in lane 1 we have GPU using backpropagation. In lane 2 we have backpropagation on my machine, a CPU. In lane 3 we have the CPU using the naive optimization method that I showed you earlier here. And then finally in lane 4 we have the naive version on the GPU. So let me just ask, are the contestants ready?
Yes, 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 yes.
All right. In that case, on your marks, get set, go. You see that the LSTM on the CPU gets off to an early lead, but oh my goodness, the GPU overtakes it, and on lanes 3 and 4, things are moving really, really slowly. So that, ladies and gentlemen, is the amazing power of backpropagation and CUDA. Thank you very much.